Okay, now we can continue our discussion. You want to continue the discussion first? Okay. Yeah.
Yeah, right. So yeah, I'll pose it in the form of a question that is there any thermal effect coupled to the rate dependency of the load?
Yes, there is a thermal effect, especially if we do a testing scenario where we have a small test bar. Then we can see if we do fast tests, of course, we get a high thermal increase. And still, low thermal increases doesn't affect this material very much. But of course, if we go up to several hundred degrees, then we start seeing effects. But a problem with running very fast tests is, of course, that the thermal strains will influence the testing. So this limits also our testing possibilities.
Thank you.
Thank you. I have a question for two of the speakers, the first and the last. Perhaps if I start with the last speaker, the R260 grade is the pearlitic microstructure is, I'm expecting, quite coarse compared to the steels that the first speaker was talking about. So one question I have is in the test material you were producing, did you see any evidence of inhomogeneous deformation within the pearlite, like shear bands forming or something, which is something you can get in a coarse pearlitic microstructure, whereas in the seals in the first paper, they're all high-strength steels, and so there's some differences in the pearlite morphology. So the question I have, I guess, to both of you, as a challenge perhaps, I'm a metallurgist, is to what extent does the pearlite morphology itself have an effect on the deformation behavior?
It's a hard question. I can start from my point of view. When we do these pre-deformations, we clearly see that there are some shear bands forming on the surface. Of course, they're quite fine in the sense that they're evenly distributed along the entire surface. But also the size of the test bars that we're using means that, at least I think, that will make it that we get an average value. We don't get the point value due to local effects. But certainly it develops shear bands, and there is an effect from the if that comes from the coarse grain structure or coarse pearlitic grain structure or other coarse structures in the material, I'm not sure, but it certainly we can see them. If you have some.
Did you want to comment on the effect of the microstructure? I know it was a little bit off the track of what you did, but on those steels, yeah.
Why we have this initiation of the project is because what we find with the impractical in the electrical railway. So sometimes we have the similar rail steel weight, similar premium rail steel weight, but the quick initiation will be completely different. So that can be in terms of the microstructure. For example, the higher carbon content will have the pole. What we find is that the pole will tattoo cementite, and there's hard and brittle, and then that can affect the crack initiation life and also crack shrinkage.
Okay.
So I have the question to the last presentation. First, yeah, I think very good work. You did, well controlled experiment and also had a very good theoretical study. So in your background, the motivation is in reality due to loading contact, cyclic loading, you have very large plastic deformation in the rail. So that's the motivation for you to carry out this experiment study. But in reality, this large plastic deformation is due to many cycles of accumulation of plastic deformation. So that means for each cycle, the plastic deformation actually is very small. But in your experiment study, this plastic deformation is applied very large, yeah? So how can you apply the developed theory from your experiment into the real situation? Can you comment on this question?
I think in any experiment you have to try to simplify the reality. In this case, of course, it's a time constraint that we could have tried to simulate smaller increments and put several loading. We have thought about it. We have some few samples where we actually tried to do smaller increments to see the effect, but we haven't gone much further with those, so I can't tell how much it affects. But I think if we want to reach the goal of having a model that can predict the cyclic behavior, we also need it to be able to predict the larger cycles. We don't want a model that is tailored to just one specific load case. So now we have these experimental data, then we will, my vision for how we could calibrate, of course, that we need to calibrate from the virgin states, looking at cycles from the virgin state. We need to calibrate from these different pre-deformation states, or rather including the pre-deformation, and then keep on cycling. And the model should capture all of these stages. Of course, the ideal, as you say, we should also have one case where we can do the cycles all the way from virgin material to failure almost. A problem, now my slide is not, but basically if we are trying on thin-walled samples to apply this kind of loading, we get buckling. If you want to have these high compressive load states that we have in the railway on some samples which is appropriate for getting the material behavior good, then we can't do it in the biaxial testing machine. So it's sort of a trade-off there, if you want to be able to replicate the exact load scenario, or if you want to be able to measure the behavior accurately. So I think we need to just try to circumvent these challenges. But it's a very good point.
May I continue this discussion? So, as I said, you did a very good work. Yeah. So, my concern is plus deformation is load path dependent, load history dependent. So, therefore, from this point of view, if you have a single loading to reach to a high plus deformation, might be different for the material to behavior from like small plus deformation accumulate until to reach to this large deformation. So that's my concern. Thank you.
Yeah, I absolutely agree. Of course it's going to be different, but that's where we hope that the sort of sound physical base for the material models will, even if we cannot get the exact same behavior, if we include the effects of the cycles when we do the modeling of, let's say, a rail, that should account for that. But as you say, it's you're hoping for it. You can never be certain.
My question is to people who work with Surus machine on twin disk testing. You use T-gamma criterion, which is obviously defined for certain operation conditions, for certain tracks. Do you consider any scale effects when you discuss material properties and results of your wear analysis, and vice versa when you interpret your results on twin disk machines towards reality? Do you consider any scale effects?
One of the benefits of the twin disk machine, the scaling down version, is when we're looking at extreme cases, high sleep, that's to our benefit because of the small disk. We can generate extreme heat really quickly, extreme conditions. On the normal rolling conditions, it is a problem. And as I mentioned earlier, it's not quite representative of what's happening in the field. There's things missing like lubricants, friction modifiers, leaves, and etc. We try to replicate as much as we can. We add with air cooling, but this is what we monitor with taking measurements every few cycles to measure the wear rate and trying to capture this acceleration, deceleration, and find where the steady state is. If we capture that correctly, we have more confidence that the results are fairly correct to represent the material behavior.
The most difference we'll get from geometric differences.
Yes, so the rolling, the twin disc machine obviously is a line contact. It's not the same as, so it's a scaled down version. It will be very difficult to obtain generic results that can be applied in all conditions. This is why we've chosen the discs and the line contact as a contact that we can control and obtain as accurate result as possible to input into our models. Yeah. Thank you.
Thank you. A question for Kerry. I have an interest in thermomechanical shelling, which you may share with me, but I was interested to know if there's any differences in the performance of those wheels with respect to thermomechanical shelling, or whether you've done any specific material tests, like high temperature tensile tests to characterize the material.
We did some high temperature tests on all the materials, just at 540C. It was about the same kind of differences we saw in the room temperature tests at 25C. No great differences that we saw.
And any difference in service with respect to the performance with thermomechanical shelling, or is it
we haven't really seen any shelling on any wheels yet, nothing visible. For the two that we've had with the large subsurface defects, we haven't cut those up yet, so that'll come at a later time, those results.
Okay, thanks.
So my question is for the third presenter. I have actually two questions. The first is about if you can comment the hardness difference between the couple of materials that you tested. And the second is about the wear measurement. Did you perform only the mass loss, or did you look further to wear scale depth? Thank you.
Sorry, just to answer the first question and then we can go to the second.
Okay.
So about the hardness?
Yeah, because you showed, I think, R260 and the R8, and you showed the image for the four materials, yes. And you showed different wear mechanisms. So if you can comment the hardness influence on this.
Yes.
It's okay. I think we better finish this question. Okay,
yeah.
Just
so
continue.
Generally, the softer materials, R260 and HT, they have indicated an increase, higher increase in hardness, and again, it's a very short depth through the material. The wheel materials have shown a higher increase in hardness, more or less constant in all cases, but nearly double of the bulk hardness of the wheel. Some of the materials A, B, and C have shown less work hardening. So these premium materials, basically they don't work harden as much as R260, for example. And with the laser clad materials, as I mentioned, they already have a higher hardness. So the increase in hardness is not as much. But there's a benefit there that there's to a deeper depth already.
Yeah, I think it's time to close session. Thanks of all the speakers, so we can have more discussions during the break. Thank you very much.